Hello again. This is lecture 2 for ARE 157. This is a pair of lectures driving off of the Vulcan machine shop examples. The first, today's, is about deciding which machines make which parts. The more elaborate multi-period scheduling with many parts will be the purpose of lecture 3. I used to combine these lectures into one. I'm trying a different approach this year, splitting the material and going into more detail about some of the cost comparisons. I've set up a specific example that we'll work with that's not inside Vulcan, but uses some of the information from Vulcan. I'm going to use a very simple coupling here that I bought at Ace Hardware in Davis a few days ago. Why I'm using that, I'll explain a little bit later. But I might say in passing that when I bought that at Davis, hardware store, I was practically the only one there. No cars are parked around downtown Davis. It must be a really frightening time to be a merchant or a restaurant in that area. But Davis aside, these are very common parts, and I had no trouble finding one like that. It'll be the basis of my example. Vulcan will be part of my examples too, but we'll use this coupling to go a little deeper into some of the cost comparisons. We'll make explicit examples of the costs, and in so doing, we'll look at issues that are related to that Wall Street Journal article that I had you all read and comment about. We'll be using some math in those examples, but fairly simple math. But we'll look at the deeper issues of mathematics in that example. We'll also be going back to look at some economics that's implicit in the example, not explicit. No machine shop is going to be talking about the economics in the way we are, but we'll start to see that the issues are latent there and indeed expressed in many of the issues before a machine shop or any scheduling complexity. And I'll show you at the end some new material about Vulcan machine shop that will get at some of these very specific issues. Let's start by reviewing Vulcan machine shop, and I'll go back over some pictures that you've already seen, but maybe a slightly different emphasis. So, Vulcan machine shop is one of the key pictures I showed the other day. This picture on the right has the machinist in front of one of the computer-driven machines. He's making a part that's on the little table there. We can't see the machine making that part because the window right in front of the machinist is closed. You can see the spatter of oil and lubricating oil that goes on to the door. It's being sprayed on the part as the metal bits are working. Metal on metal is a tough business. The computer part is inside, but also the area of the right over the right shoulder of the machinist. The machinist appears to be doing some other work, which is typical. Often the parts in the deburring, that is where there's an edge of metal, and he might smooth that down while the next part is being made. This is the typical operation. We looked at some other parts the other day. Here was one that was part of a production line of 67. And that was important to us because I had some paperwork about this particular part. It's being made in 3 steps, 3 stages, on 2 different machines. The Morisaki machine was being used twice, and then the machine number 41, the Hosfit axle, is being used for a final set of machining. What was important for us was these numbers in the columns, that like 5H, 7M, so on. That means that the setup time for that first stage is estimated to be 5 hours, and the runtime per part is 7 minutes. The total there should equal 67 minutes, 67 times 7 minutes plus the 5 hours. That looks more or less right. That 7 minutes is almost surely the right number because this has been programmed before, and they can measure at Vulkan quite closely how long it takes to make a particular part. The setup time is probably more an estimate. If the technician, that is the machinist, can get everything ready under 5 hours, it's time saved. What's involved in the setup is getting the bits that will be doing the machining. They're in a central storage area. Getting this program ready, getting it set up in the machine, and getting the area where the part will be put in the machine exactly right. This has to be quite precise. So in that first stage, it looks like it takes 5 hours. The second stage with the same machine will take another 6 hours to get everything ready for the second stage. Then all those parts move to another machine, which takes 4 hours to get ready. There's a batch processing going on here so that we can sum up and see what the length of time is for the total production. Obviously, it stops overnight. Obviously, if the house number 5 isn't ready, it can be delayed a little while, whatever. Here was another part we looked at the other day, rather complicated one. This is a production run of 220 of this particular seat valve for Paul Corporation. And the particular place where it was working, machine number 32, the setup time was 6 hours, and the run time was 9 minutes and 20 and a quarter of a minute. I think it's in not seconds there, but fractions of a minute, and it's using that particular program. So the big point remains that there's substantial setup time and there's run times, and you can see from this example that running the 10th one of these parts takes the same runtime as the first one or the 100th one. It's a constant runtime, and that's very typical in these kinds of settings. You don't get faster at it as the machinist or as the machine, nor do you get slower. It's the same amount of time always. With those actual examples in mind, let's switch to my rather more made-up example to see something about what machines would be used to make a particular part. There is a choice there, and this particular part that I bought at Ace Hardware will show you something like that. This is a coupling, as I said. I bought it in the plumbing section. There are many parts like this. Why I bought this one is it's symmetric. It's got threading on the two ends. So it can be made in at least two ways. The first way would be to put the part in and have the machine tool do the threading on one side. The machinist, when that was done, would take out the part, flip it around, and use the same program to make the threading on the other side. Or you could do it with a more fancy machine that has this cutting device on both sides. They're called spindles, the way the part comes in, and that spindle could be simultaneously working on both ends. And so take only half as long to make the part, but you need a fancier machine to do that. This particular part, you can see a little bit better here, is made out of a tube of steel. Perhaps the length was cut, but more like by the machine that was doing the threading. More likely that was done previously in another stage of production. This is not a very fancy precision machining job. This would not be something that Vulkan would be doing this particular part, but versions of this Vulcan would be doing if the threading had to be incredibly accurate, which it might be for some medical equipment. For basic plumbing, that's not necessary. But it's the type of part that is very useful here. So let me use that example. And I'm making up some numbers here just to try to make a contrast. So the key choice is, do you use a one spindle machine if you're the production scheduler, or a two spindle machine? I've suggested already that the runtime per coupling, that is, would be, let's say, 8 minutes for the one spindle machine, and only half that on the two spindle machine, because two parts are, the two threads are being made at the same time, so half the time. The setup time, though, is important. I've sort of just made up the numbers, but it's the relative ones that will matter for our exercise here. Presumably, we'll say the setup time for the one spindle machine is 60 minutes. Would it take under 60 minutes to set up the two spindle machine? Almost surely not. It's more complicated. We got to get 2 bits in. Does it take twice as long? Maybe even longer. I've got it as 1.67 times the 60 minutes, another 40 minutes, thinking that, well, if you have to, as an operator, go get the cutting bit, you could probably pick up 2 at the same time. Wouldn't be that difficult. Maybe you save a little bit. Whatever, this is a plausible number, and we'll see where that leads us. The first thing to think about is the time that it takes to make these parts, and let's look at them as a function of the number of parts made, which is the next diagram. So on the x-axis is the number of parts in the production run. Obviously, if you just make one part, it's going to take a lot of time because you got all the setup time. You got more setup time on the two spindle machine, as I just showed you, and less setup time on the one spindle machine, but the run time is greater on the one spindle machine. The slope of these lines is the run time, which is less for the two spindle machine by the way I've constructed it, in fact, half. Why have I used little squares instead of a nice straight line, even on these straight lines? Well, because it's hard to imagine making 20.5 or 20.3 couplings. You either make a whole coupling or not, so technically they're integers, and so I want to emphasize that. But of course, we could have just used a line. If you just measure in terms of time, you can see where these lines cross, someplace around 15, that if it's more than an order of 15 or a production run of 15, it would make sense to be using the two spindle machine. It uses less time than the one spindle machine. Whereas if you're making a relatively few number, 15 or less, you would make the one spindle machine. That's measured in terms of time. But time is not what a production scheduler would think about, or an owner of the machine shop. That person would think of costs. So let's expand this idea and look at the various costs of the machine. My next slide here expands on the setup time and the run times to include costs. Let's look more closely at the bottom column here, the machinist wage per hour. As I mentioned in Vulcan, and as our Wall Street Journal article suggested, the more complicated the machine, the more likely it needs a fairly well-trained machinist who probably commands a higher wage per hour. So I made up a number here that the one spindle machine operator gets $15 an hour, and the two spindle machine operator $20. Obviously, that operator could also operate a one spindle machine, but presumably the ones scheduling this are looking at how to minimize costs would try to use the less expensive labor. But there's some other costs that have to be considered when you're running either a one spindle or a two spindle machine. The machine costs something. Somebody, presumably the owner of the machine shop, had to pay for that machine, and it's sitting there. If it's sitting there, it's still costing something in terms of the interest expense on the machine, on the initial investment. If you take that a typical working year is 2,500 hours, the monthly interest expense is what I've shown in the next to the bottom row, because the machine of a one spindle variety is less expensive initially. I'm going to say that's $11.20 per hour, where the two spindle machine is $16 an hour. When the machine is actually being used, not just being set up, the machine is wearing out. And I've captured that by saying after 4 years, the machine would be sold for $300,000 if it's a two spindle machine, and $227,500 if it's the one spindle machine. So I've made a 40% drop in value if it's used 10,000 hours, and that works out to be $20 an hour of per use if it's the two spindle machine, and less if it's the one spindle machine. And I've made the sale price of the one spindle machine not 40% down, but 35% down, on the theory that the fancier machine wears out faster. It's got two spindles. Either one of them might go out of alignment, and to make that machine worth much less. So I'm saying there's a deterioration of costs, there's an opportunity cost or an interest expense on the investment in the machine, and that also is relevant to the machinist's wage. This is the issue that was in that article, and many of you noticed that you said it was just the wages that determine what's the right pricing here. You had, in that example, the fancy machine cost had a labor wage rate of $25, and the old style machines $10, and you said 25 to 10 is the ratio. But you also have to consider the value of the machines to some extent. It's true from a day-by-day operating perspective, the machines are there, there's some costs, but if the machine shop owner doesn't consider the deterioration and the interest expense on these, that machine shop doesn't stay in business very long. And this is quite important in consideration. So putting all these factors together, we can go from time to costs, and that's what I've got in this diagram. It too has two lines, one for the two spindle machine and one for the one spindle machine, as a function of the number of parts being made. That is very linear again, because the cost per part, whether measured in the labor cost or the deterioration cost or the interest cost, is a linear function of the time, just not pure time. It's these cost factors. So the one spindle machine, when we put it into costs, has a lower setup cost in proportion to the cost of the two spindle machine, because that two spindle machine had to be set up by a more expensive labor, and it was more expensive to begin with. But we get the various patterns that we see here. When we put it in cost terms, we can notice that these lines cross at 25 if the order is 25 or larger, it should be made on the 2-spindle machine. If it's under 25, it should be made on the 1-spindle machine. It's more cost effective to do that. Well, there's the story. And I've compared 2 ways of making the same coupling with that conclusion. But there's a lot more behind that, and that's what I want to use this example for. Well, let's start with some of the math implications here, or the math perspective on this problem. It starts with this very same diagram, the cost of making couplings. I've said that the lines cross at 25, and that's where you first see a little blue under the pink. Well, look at 24. There's a little blue over the pink. At 26, there's a little more blue under the pink. 23, symmetric with 27, has a little more blue, a little less blue, right? Well, what does it mean to have a little less blue or a little more blue? That's measured in what, maybe cents or something like that. It is cheapest to make 25 on the 2-spindle machine, but more fundamentally, over this range, say 23 or 27, it doesn't matter very much at all which machine is used. If you're making 40, there's a substantial cost savings to use the 2-spindle machine. If it's 10 that you're making, there's a substantial cost savings to use the 1-spindle machine. But in the intermediate range there really isn't that much difference. Now, why does that matter? Well, it matters in the sense that we've been spending a lot of time in 100A and 100B trying to teach you to think about optimization. I'm suggesting this is an optimization problem of a sort. Which version of the machines to use, the 2-spindle or the 1-spindle? But it happens where the optimum is, the objective function is pretty flat. It doesn't really matter what we do here. It's very clear to see if the objective function is very peaked. Well, the optimum is this one thing, you ought to do that, or you're a foolish owner of a machine shop. Over this range, no. 23 to 27 is about the same, especially if you have to think about other considerations or even guessing what's the best thing to do. It's going to be hard to measure it. From an economist's perspective, that means it'll be very hard for us to tell that someone is close to the optimum of a decision, but not at the optimum. And that's quite important. We'll find that's quite typical of these kind of problems, these scheduling problems, these network problems that we'll deal with. Contrary to the impression we give you in 100A, the optimum is not obvious often. We'll see in some other problems, in fact, it's very hard to even know that we've gotten to the optimum. Here we do by where the 2 lines cross, but they're crossing not very clearly, are they? All right, some more math is revealed by this next slide that I've done and the experiment that I've made to make it. I thought about this question. What if there was a different setup time for these 2 machines, although the same proportion? So I consider not the 60 minutes setup time for the 1-spindle machine, but 50. I get 2 different lines like I did before, and I find that they cross at 21. I also did 17. 17 is the implication of 40. This is 29. This is 33. Well, here's a question. Would it be worth my time to consider a case where there's 65 minutes of setup time and in proportion for the 2-spindle machine? I don't think so. I think you can guess what that number is, since it's actually a line that's going on here. How did I get these numbers? Well, I have to tell you how I got the previous numbers. Let's go back one. How did I get those numbers? Well, I created an Excel spreadsheet. I had a column that went from 1 to 40, and I put in the formulas, first in terms of time, and then in terms of the other costs, and I used these numbers. I just put them in an Excel spreadsheet, then dragged down those formulas to have them go from 1 to 40. Copied those numbers and put them in those figures I just showed you. Right? I could have written all of these numbers as letters, say, so machinist's wage would be W1 and W2 for the 1 and 2 spindles. I could have made an abstract like that, but I've used actual numbers. That's because I want actual numbers in these figures. I want to know that it's a crossover at 25 rather than there is a crossover. I can guess there is one without doing all the math, but I want to know the exact number. And that's to say, in a diagram like this, what's the order size favoring the 2 spindle machine? It's 25 versus 21. I want an actual number. What I've done, a mathematician would call numerical methods. I've made the whole thing start with numbers, and I wanted an actual answer. But I could have been a mathematician who wrote it in symbols, such as the W1 and the W2, and I could have maneuvered all that around and gotten a formula that said what is the crossover point between those lines, that is, where is the order size. Is it large enough that you would have to use the 2 spindle machine after all? I could have done it algebraically or analytically, more generally, but I did it numerically. But that leads us to think about what is this relationship that I plotted in this graph? 17, 21, 25, 29, 33. It's a line, but it's not, my question isn't that it's a line, but what is it mathematically? If you think of the analytical solution, I'm saying where's the crossover point is a function of all those parameters. And I'm asking, how does that crossover point change with one of those underlying parameters, like W1, or here the setup time? From a mathematical perspective, this diagram shows a partial derivative. How does something change with respect to? Holding all the other things constant. That is a partial derivative. You are used to doing partial derivatives analytically, fine. I said you could do this analytically in this case, but I've done it numerically. There'll be many problems we look at, though, many systems that we'll study, that there is no analytical solution, but we can simulate them numerically and get the numerical partial derivative. Once having the partial derivative, you could go further, you could get the second partial. And since this is a line, that's not very interesting, but it might be in other cases, it might be a very curved partial derivative. My point is, from a mathematical perspective, we're doing something that's very familiar, except it's hidden in these types of calculations. Some other things might be hidden too, and let's go back to the key part of this, which is where I set up some things. I want to discuss that. The economist in me wants to. Well, actually, speaking of economics, maybe there's a point to be made here. These are 2 graphs. I remind you what they are: total cost. You have done many exercises, I'm sure, where you've gone from total cost to marginal cost, taking the derivative of the total cost function with respect to the number of couplings. This one is very uninteresting since the total cost function is a line. It is a constant marginal cost. lower for the two-spindle machine than for the one-spindle machine, which is to say those lines have different slopes. You've also been well trained to take average costs, which is dividing the total cost by the number of the machines. You could do it at 10 or 20 and so forth. Think what those plots would look like. Obviously, because of the setup costs at one being made has a very high average cost, much higher than a 20 and certainly higher than 40. The average cost curves are sloping down, that is, asymptoting to the marginal costs, which are these constant. I believe we've drilled into all of you, especially in 100B, that when you see marginal costs below average costs, that's usually a situation where you expect natural monopoly. There's no natural monopoly in a little machine shop. There is differences in average costs and marginal costs, though. We're right to emphasize natural monopolies, and that's in a huge system, say the natural gas pipeline system in all of California. We're not going to add a second system. And the cost of a little more gas going through that system is relatively small compared to the initial cost of setting up the whole pipeline system. That's probably a natural monopoly. But every production process has some setup costs. I believe I can say, and you too will confirm, that the setup costs of online teaching are substantial, and none of us is collecting a monopoly rent from that, are we? But the mathematics of this kind of setup cost is very interesting and very difficult. Derivatives aren't sufficient to decide what's the right thing to do. You need to know something about, well, in this case, it would be mathematically the intercept, right? The marginal cost of the two-spindle machine is lower than the one-spindle machine. That analysis would say always use the two-spindle machine, but no. The intercepts are positive, which is to say they're setup costs, and we've got to consider that. What that means for a machine shop owner is if their pricing's such or doing an order on the wrong type of machine, they will not be in business very long. They have to cover their average costs as well as their marginal costs. Let's look at some other economic features that I assumed here. If this would have been in class, you might have raised your hand and said, well, why are you doing that? You didn't get the chance to do that since this is just me lecturing. But I want to come back to some very important economic concepts here and where we get some of these numbers. I asserted that, Vulcan being typical, the fancier machinists, the ones better trained, the ones able to use the fancy machines, earn more per hour than some other machinists. That's what I tried to capture, 15 and 20 here. But you should rightly say, well, wait a minute, those machinists aren't just working for that 1 hour or even on that one part for a couple of hours. There aren't machinists standing outside Vulcan machine shop waiting for an afternoon's work at either $15 or $20 and have to be paid. No, those machinists are on the payroll. They've surely been hired for the month, if not the year. And so the machinist's wage of $15 and $20 is irrelevant. It's just they're not there. But that thinking we have to be a little careful about. We're not just making couplings in this machine shop or any other of these multi-product firms. We're making many other things. And that machines could be used elsewhere. And what you would like to imagine is that that machine is used elsewhere is at least what he's being paid, the $15 or the $20 as the case may be. You'd like to, if you're the machine shop owner, hoping that you're going to make a little bit more off the parts you are selling than the machinist's wage, but you'd at least like to cover that amount, and you're covering it by assigning the machinist to other tasks. So a reasonable estimate of what that cost might be worth elsewhere is what you have to price in for the one spindle or the two spindle machine. There isn't an explicit market for the machinist, that is. You're not hiring them off the street for that hour, but that's what you ought to cover all the time. They have an opportunity cost, an economist would say. The machine shop owner is saying, I got them here, I might as well have them doing something, right? It's an opportunity cost concept. It's also, is there a market there? Well, on this level, no. You've been taught at 100A to think of capital as inflexible, but you can hire workers as you need them. In these examples we're looking at, that's not even true. Everything is fixed. But since they could be doing something else, they have an opportunity cost. That argument is even more to the point about the machines themselves. It's plausible to, the interest is going to be paid regardless, but if the machine shop owner isn't at least covering those interest expenses, that machine shop will not be in use very long. Likewise, the deterioration has to be considered. If a machine is just been bought and it is sitting in a machine shop and never used, it was not a very good investment. But there's a little more subtle idea comparable to the machinist here. The machine shop owner presumably can find other things to do with either a one spindle machine or a two spindle machine. And if have many other parts to be made, sensible scheduling would at least cover these costs. If you could rearrange where the machines are used, you should find that they at least do this while making something else. If they can do even better, you make a profit at this, but this is sort of your minimum costs and so on. And what I'm arguing here is that there is effectively a market for machines, even when there isn't one. The machine markets that I've assumed is a new machine market and a 4-year-old machine market. And in a way, I'm saying hour by hour, there's a market for machines because they could be used elsewhere. This is entirely an opportunity cost concept. Maybe another way to look at it would be that from a mathematical programming perspective, which you've all encountered in ARE 155. We're making so many couplings, they're selling at a particular price. We're making other things too as a machine shop. We have these non-tradable inputs, the machines and the machinists. We allocate the best allocation of the machines and the machinists across a number of parts and probably more machines than I'm showing here. And we can deduce from that what was the shadow price of those particular activities, making those couplings on those machines. And the shadow price is the implicit value of those machines. You'd like to think as a machine shop operator that the shadow price, the use you get out of the machines implicitly, is at least the costs of the machines, which are the deterioration or the interest. Otherwise, you don't stay in business very much. Either way we look at it, it's if there is a market in machines. Now, you can't buy and sell a machine for an hour or lease it more accurately. And you can't add it to the machine shop floor in an hour, but you see that there's an opportunity cost concept. We'll see in many, many of the examples that there is implicitly a market for something, and it's saying what is a shadow price, sometimes high, sometimes low. And this will be a key analytical device that we will use in this course. I'm not saying that a machine shop operator uses that terminology. He might use something very different, but we as economists can use the concepts of opportunity cost or shadow value. It's just a different term for a concept I believe is quite common in machine shops. And to show that, I'm going to go back to Vulcan, and we're going to look at some of the other material about Vulcan and see if we see anything from this very specific example with the couplings. I showed you this picture before. This is a set of flanges being made. It's very complicated parts. Showed you that there are 25 being made in this production run. This outlet flange is going to Paul Arrow, one of the major customers of Vulcan. I don't know that we discussed it before, but what is Vulcan's role in this? It was just to do the machine, the trimming, and the making the holes in it, as you saw in the previous picture. The full paperwork of this part said that Paul Arrow supplied the castings. Those were the raw pieces of steel. Vulcan didn't buy that. That shape was done in a casting. Vulcan did all the nice polishing and so forth. And Paul Arrow is to do the passivating, which is a final cleaning and getting it ready to be used in its parts. That isn't being done by Vulcan. They're just doing the machining. And this part was interesting because of its substantial setup time and very long cycle times too. This is a complicated part to make, as you can see from that previous picture. And why I'm referring back to this one is this diagram that I had made and shown you before, which is the cost in terms of time. I didn't try to put it in terms of dollars for those outlet flanges. And remember, it lined up very closely with what my brother had bid on the purchase order, the initial purchase order. He had given a set of quotations that declined in price per flange the bigger the order. I'm just plotting the setup times and the runtime here. You see, it's what I've got here is the average hours, comparable pretty close to the average cost, and the average hours, average cost is declining. That's that downward sloping average cost curve that we've talked about before. It's right there. It's implicit in the setup times in that equation, 23.75 hours plus 1.3 hours per flange. It's there, it's in the quotations, it's everywhere about this machine shop. Some of the other ideas I just talked about are also around Vulcan. Here's a diagram you haven't seen before that I took again on the 15th of June of 2015. This was on a bulletin board, and it was that day's attendance, the number of people working as a machinist. So Wayne, Melvin, Jack, Bruce, and so on, right? And you can see the next column over, the machine they're working on, and the company that the part's being made for, and the description of the specific thing they're doing. Almost everybody has something that they're doing, except Bruce, Bob, Gary, and Pat weren't there that day. Two of them were on vacation, and two were out. Presumably, the vacations have been planned a long time ahead, and the scheduling coordinator, my brother that is, knew what to do about that, but probably the outs were a surprise to him. Might have been out the day before, too. Might have been sick, and it told him, but he probably had to go around the schedule. From a scheduling perspective, that is, there was some uncertainty in all this, also uncertainty due to when customers might want things. But we'll see when we get into lecture 3 just how hard it is to even schedule things under certainty. But why does this relate to my example with the coupling? I was saying, well, you sure want to keep the laborers all working. You're paying them. And down that final column, except for the yellows, there are only 2 that aren't working on a specific job themselves. The first one is Melvin, and I can't even read what he's doing. And then way at the bottom is Mark, the very last one, and he seems to be helping. I can't read that, as I've complained before. My brother's handwriting is terrible, but he's presumably helping somebody, so he's really on a machine too. But everybody else is running their own jobs. This day, and I believe it's typical, almost everybody is doing something, which means they ought to be earning at least, or providing a value equal to their wage rates. At least that, you would hope. There's a similar diagram on a bulletin board for what the machines are doing. And so you can look ahead what they're up to. Often the bulletin boards show the workers what they would be doing next. They were probably interested in that. The machines could have cared less and didn't even know what they were doing, probably. We can't read this too well and take the picture very well, or it wasn't very flat on the bulletin board. But another one is quite legible, and this is a particularly interesting diagram. This was the backlog as of June 10th, 2015. This is a weekly report generated by some of the software available to Vulcan, and it showed how far ahead particular machines were scheduled, meaning what the backlog was, knowing the production scheduling that was going to show probably through the end of June. And there's substantial differences here. The number 45 Haas machine had only another hour and 25 minutes of work scheduled, whereas the number 46 horizontal had 69.75 hours and was 2 weeks to go. Why is this important? It's relevant for if you're deciding to bid for other parts. Usually this is done 2 or 3 weeks in advance, or maybe you could say, well, let's just make this other one. We know it's going to be bought next month. You move up the schedule because it primarily uses the 45 Haas machine. Why not? That machine would otherwise be idle. You want it to be working. You don't want to bid for a new part that puts a lot of more demand on number 46 horizontal that's already busy. That is to say, from this diagram, it would look like the horizontal one has a higher opportunity cost, a higher shadow price, can I use that terminology, than the Haas machines. And so if you're bidding, you should try to account for that possibility. My brother, or anybody in the machining industry, would not be using the term opportunity cost, let alone the term shadow price, but they certainly would say that machine's busy, or they would say we have a real backlog, that's what this diagram is titled, or we have a lot of congestion, that's another way of putting it. Those words are the same concepts. If you want to think of shadow prices as that there's a lot of backlog, fine. That's a good way to think about it. Suppose you looked at these diagrams like this week after week for some months, you're the machine shop owner, and there's always a backlog on 46, the horizontal. You could not try to make parts that heavily use that machine. You could also say, well, at that time scale, maybe I should buy a new machine, new horizontal number 46, or equivalent machine, or one that could do some of the same tasks that that horizontal machine did. That sounds good. Well, the problem is, and we'll get into this in more detail in some other examples later in the course, is machines don't come in quarter machines or half machines or 3/4 machines. They come in units of machine. You could buy a second 46 horizontal and suddenly discover that half the time, or 3/4 of the time, one of them isn't being used. Wow, that's costly. You needed a little bit more horizontal, but not a full machine horizontal. That makes the decision harder. So to go back to some math, I've already alluding that these could be viewed as mathematical programming problems, but given at the level of how many machines you have, how many workers you have, maybe 25 workers and 10 machines in Vulkan Machine Shop, addition of one more worker, but even more, one more machine of a particular type, that is a mixed integer programming problem. That is, the integers matter. It's 1 or 2 and 3. If it's 3,117 versus 3,116, yes, those are integers, but you might as well say it's continuous. It's not continuous when you're going from 0, 1, 2, and 3, something like that. Turns out the math of that no longer uses derivatives. It uses mixed integer programming, which is much, much harder mathematically. Mathematicians love those problems. I'm not sure the machine shop owners do, because they have to make a big investment, and maybe they don't get very much for that investment. At that scale, they're doing mixed integer problems, but they're also trying to do a scheduling. And I go back to my brother's handwritten spreadsheet about his scheduling that June. It's only one of 3 pages. And he's got the columns for the machines, and he's got the parts. He must have had in his head which workers could have done which jobs. There's another dimension, a third dimension to that spreadsheet in his head, but most of this was in his head about what could be done what, and he's trying to solve a very complicated scheduling problem. That will be our discussion for lecture 3. I hope this lecture 2 has brought home the importance of those setup costs, and there are assumptions about what markets exist in particular settings. Those will be themes through many, many of our examples this term. So go back and review some of that, especially those of you who answered that it was only labor costs that were determining which was the better way to set up that machine shop in Illinois. Think about why you answered that way. It's not wrong, it's just missing something. How about if we say that? Farewell. I'll get lecture 3 ready very soon, and I hope they will make a nice pair for you. Goodbye.